Welcome to this explainer. You know, right at this very moment, an epic, invisible tug of war is happening inside the device you're using to watch this. It's this relentless, high-stakes balancing act between lightning-fast performance and massive storage space.
I mean, really think about it for a second. How on earth does your machine instantly process a complex 4K video edit while simultaneously acting as this permanent vault for hundreds of thousands of your photos, documents, and apps? It's honestly a miraculous feat of engineering, and it relies on a really strict, brilliantly designed hierarchy of memory.
So, here is our roadmap for the explainer today. We're going to cover four main areas. First, the hardware's hidden software. Second, the need for speed. Third, the great memory trade-off. And finally, measuring your digital world. Okay, let's jump into section 1, the hardware's hidden software. Before your hardware can store a single photo or even load a web page, it actually needs to wake up. And that's where firmware comes in. You can kind of think of it as your hardware's basic instincts. It's software, sure, but it is permanently embedded right into the physical device itself. Without it, your computer components are literally just expensive paperweights that have absolutely no idea how to talk to each other. It is the foundational spark of life for your system's brain. Moving right along to section 2, the need for speed. All right, so once the hardware is awake, your central processing unit, the CPU, takes the wheel. And let me tell you, the CPU has an absolute insatiable hunger for data. To feed it, we use CPU registers. These are incredibly compact, hyperfast storage pockets situated directly inside the microprocessor itself. It's exactly like the CPU's own hands, physically holding the specific pieces of data it's actively working on at this exact millisecond. But, just like us, the CPU's hands can only hold so much. Enter cache memory. Think of cache as the top of your physical desk. It holds the documents you're actively reading right now, as opposed to files buried deep in some basement filing cabinet. It's a high-speed middleman that sits right between the primary RAM and the CPU. Its overall capacity is tiny, but its job is absolutely vital, keeping frequently used data instantly accessible so your ultra-fast processor doesn't have to just sit around waiting. This setup creates a beautifully efficient three-step search sequence that happens billions of times every single second. Check this out. Step 1, the CPU needs data, so it checks the ultra-fast cache. Step 2, if it's a miss, it reaches farther out to the main RAM. Step 3, once it finds it, that data is copied right back into the cache for next time. This exact rapid-fire sequence is what keeps your device from freezing up when you open a heavy new application. Which brings us to section 3, the great memory trade-off. Now, you might be wondering, if cache and registers are so unbelievably fast, why isn't all memory built exactly that way? Well, it essentially comes down to a harsh engineering reality: cost and physics. We actually have to divide our computer's brain into two distinct camps. Primary memory is your main workspace. It communicates directly with the CPU for instantaneous access. Secondary memory, on the other hand, acts as your massive but indirectly accessed auxiliary backup vault. The trade-off becomes completely obvious the second you look at the economics. Primary memory, like your RAM and cache, is incredibly expensive to manufacture, which is exactly why your phone might only have, say, 8 gigabytes of it. It's also permanently fixed inside the system. But secondary memory flips the script entirely. Hard disks, solid-state drives, flash drives, they're cheap, which allows for massive storage capacities, and they're highly portable. You are fundamentally trading lightning speed for vast, affordable space. Ultimately, their daily jobs are just completely different. Primary memory lives entirely in the present moment. Because things like RAM are considered volatile, they suffer from total amnesia the second the power turns off, which is exactly why your heart sinks when your computer crashes before you've hit save, right? Secondary memory, however, is strictly non-volatile. Its sole purpose is to permanently safeguard your data, power or no power. And that leads us to our final stop, section 4, measuring your digital world. To really grasp the sheer scale of modern storage, we kind of have to start at the absolute bottom, the bit. A bit is just a single binary digit. It is the smallest unit of digital existence, representing nothing more than a 0 or a 1. Every single Ultra HD movie, massive video game, and complex application you own is fundamentally just a vast, seemingly endless ocean of these tiny on-off switches. And from that single bit, we start climbing the multiplier ladder. 4 bits make a nibble, 8 bits make a byte, which is roughly the equivalent of one single character of text. From there, we multiply by 1024 to hit a kilobyte, then a megabyte, then a gigabyte, and finally a terabyte. This is the scale you and I interact with every single day. A few megabytes for a high-res photo or a terabyte for your entire laptop's hard drive. But the scale pushes into truly mind-boggling territory very, very quickly. 1,024 terabytes gives you a petabyte. And if you jump all the way to the top of our current measurement scale, skipping a few steps in between, you hit the yottabyte. That is 1,024 to the 8th power bytes. To put that completely astronomical number into perspective, if a single yottabyte were represented by pennies, it would create a stack that could reach the sun and back several million times. Crazy, right? So we've seen how meticulously your machine balances the immediate, high-speed needs of the CPU with a vast, permanent vaults of secondary memory. But as our digital footprints just absolutely explode and human data generation starts being measured in yottabytes, how massive will our need for cheap secondary storage ultimately become? And perhaps more importantly, how will future engineering evolve this great memory trade-off to keep up?